All right, welcome back. This is your video for week 10, day 2, normally scheduled for Friday, March 27th. There are a few things due today. One of them is daily homework for week 9, day 2, the lecture from before break that I posted just a couple days ago. And the other one is for Monday's lecture, the daily homework, week 10, day 1. Test 2 on Moodle is also due today. If you have not already emailed me a PDF copy of your work for the daily homeworks, contact me now to work out how we can make that happen or to request an extension. Test 2 is due today on Moodle, and if your attempt was not completed, it was automatically submitted. If this is an issue, contact me and we can figure something out. Due next time, by Tuesday at 1 p.m. Earlham time, is periodic homework 5 and the daily homework for today, week 10, day 2. Periodic homework 6 will post on Tuesday when periodic homework 5 is due. So that's everything as far as announcements. I hope everyone is staying safe and sane, but on we go with our physics. And today we're going to talk about a few things related to the Legendre polynomials. The Legendre polynomials being the solution to Legendre's equation, which I may as well write up here at the top as a reminder. Legendre's equation was 1 minus x squared quantity times y double prime minus 2xy prime plus L times L plus 1, y equals 0. And last time we found some solutions to Legendre's equation by assuming a series form of our solution. And we discovered one of the solutions of Legendre's equation, which is the Legendre polynomials. And today we want to talk about a few of the features related to Legendre polynomials. The first of these features is something called the generating function. There we go. So this is the generating function for Legendre polynomials, given the variable capital phi, and it is a function of, for now, x and h, and it has a value of 1 minus 2xh plus h squared, all to the negative 1/2 power, where h is between 1 and negative 1. And this generating function will have a few uses that we'll get to as we move through this video, but one of the first things we're going to do is we're going to show that this generating function, phi in terms of h and x, can be written as a linear combination of Legendre polynomials, meaning we can write this as a sum from L equals 0 to infinity of h to the L times PL of x. Or, in a different form, P naught of x plus h times P1 of x plus h squared times P2 of x, and so on. And there are a couple of ways we can do this, some more formal than others, and we're going to start just by taking our standard binomial series approximation. So we can show that phi, our generating function, or we can just define it to be 1 minus y to the negative 1/2 power, where y is just going to be taking the place of 2xh minus h squared. So using our binomial series from way back in chapter 1, we can show that phi is equal to 1 plus 1/2 y plus 3/8 y squared, and so on. So if we now replace y with 2xh minus h squared, we get 1 plus 1/2 times y, 2xh minus h squared, plus 3/8 times y, 2xh minus h squared, again, that whole thing squared, and we could write more terms if we want to, but that's as far as I'm going to go. And I'll leave the algebra for you to do on your own, but eventually, after some simplification, we end up 1 plus xh plus h squared times 3/2 x squared minus 1/2 plus, and so on and so on. And, well, 1 is just p naught of x plus h times, well, x is just p1 of x plus h squared times, well, 3/2 x squared minus 1/2, that's p2 of x, the second order Legendre polynomial. So this obviously isn't a formal mathematical proof, but we have at least verified through the first 3 terms or so that we can write our generating function phi in terms of Legendre polynomials. We should check to make sure our generating function satisfies some of the normal things that we want Legendre polynomials to satisfy. If the generating function really can be written as a linear combination of Legendre polynomials, then it should have some of the same properties. And one of those properties is that PL of 1 should always equal 1. So let's verify this one. So here we want to check on the value of phi when x is 1. So we can leave h in there and plug in x as 1, and we get the following expression. 1 over the square root of 1 minus 2h plus h squared. And, well, 1 minus 2h plus h squared, this is just 1 minus h quantity squared. And the square root of that is then just 1 minus h. So we have this is equal to 1 over 1 minus h. Now we can once again use our binomial series, because this is just 1 minus h to the negative first power. So using our binomial series expansion, we get that phi with 1 for x gives us 1 plus h squared plus, and so on. So kind of matching this with the form that we saw before. Oh, why did it do that? Matching this with the form we saw before, well, we have 1 times p naught of 1 plus h times p1 of 1 plus h squared times p2 of 1, and so on. Which means that each of these Legendre polynomials evaluated at x equals 1 must have a value of 1 if they're going to match with this form we just showed up here. So it looks like our generating function does give us a value of 1 for our Legendre polynomials. We still have these factors of h because the generating function isn't just Legendre polynomials, it also has this h to the l term in there. But all of the PL of x terms have at least become 1, which is what we wanted to check. The last thing we want to see here is that our generating function is a solution to Legendre's equation. As we've seen from other aspects of math and physics, if some function is a solution to a differential equation and some other function is also a solution to the differential equation, then any linear combination of those two functions should also be a solution to the differential equation. And since the generating function, we are claiming at least, can be written as a linear combination of the Legendre polynomials, that means that the generating function should be a solution to Legendre's equation. So we're going to plug our generating function in for y into Legendre's equation up here. So if we do that, we end up with the expression 1 minus x squared times the sum from L equals 0 to infinity of HL P double prime L of x. So this is just what happens when you take two derivatives of y. It doesn't affect the h to the L term because that's not in terms of x. The derivative is only applied to the part of this expression that is in terms of x, part of this expression, which is specifically the PL term. So next term up, minus 2x times our first derivative of y, which is the sum from L equals 0 to infinity of HL P prime L of x. And last but not least, the last term here is just a nice constant term, L times L plus 1 times PL of x. There should also be a summation sign here. I missed that in my notes. Still with the HL PL of x, no derivatives this time because this term just has a y, not a y prime. And all of that equals 0. So, in order for this equation to equal 0, then that means this equation must equal 0 for each power of h to the L. So for each value of L. Because if we want some number times h plus some number times h squared plus some number times h cubed to equal 0, each of those numbers individually have to be 0. So we can just kind of take out these HL terms and these summation terms. And our expression still has to hold true. So we have 1 minus x squared times PL double prime of x minus 2x times PL prime of x plus L times L plus 1 times regular old PL of x equals 0. So this is Legendre's equation with PL of x plugged in for y. So that means, well, obviously Legendre's polynomials satisfy the Legendre equation. So we can say that because we know that PL of x satisfy Legendre's equation, we can also say that our generating function, phi of x and h, also satisfies Legendre's equation. So we've shown a couple basic facts about the generating function. We've shown, at least term by term, that it can be written as a summation or a linear combination of the Legendre polynomials. We've verified that by taking a binomial series expansion. We checked that the generating function confirms what we know about Legendre polynomials, that they have to have a value of 1 when x equals 1. And we verified that our generating function is a solution to Legendre's equation. So why do we care? What does the generating function help us do? And there's a couple of things we can look into here that might be useful. So let me clear this all off. One of the ways in which the generating function can be useful is in determining things that are called recursion relations. Recursion relations are things that, one, can be derived from our generating function. We're not going to go into exactly how this is the case for today's lecture, but just know that they can be derived from the generating function. And what recursion relations are ways to relate the Legendre polynomials to other Legendre polynomials and their derivatives. In short, some of the recursion relations can relate a Legendre polynomial PL of x to the two previous Legendre polynomials, PL-1 of x and PL-2 of x, or relate a Legendre polynomial's derivative to the value of the Legendre polynomial itself. And I'm just going to state some results that are in your book as some recursion relations as examples. One of them is that L times PL of x equals 2L minus 1 times x times P sub L minus 1 of x minus quantity L minus 1 times P sub L minus 2 of x. So, in short, let's imagine L is 3. We can now find a formula for P3 of x in terms of the formulas for P1 of x, or P2 of x, and P1 of x. If we want to find the formula for the 100th Legendre polynomial, well, if we know the formula for the 99th and the 98th Legendre polynomial, we could use this recursion relation to find it. And this is just an idea of what the recursion relations do. This recursion relation relates the derivatives of two Legendre polynomials to the current Legendre polynomial. So, if you want to know, for example, what P3 is, you can find P3 by looking at the derivative of P3 and the derivative of P2. Other examples, I'll just write them down now. PL prime of x minus x times P prime of L minus 1, note this prime here, of x equals L times P sub L minus 1 of x. Another one, 1 minus x squared, PL prime of x, meaning the derivative, equals L times P sub L minus 1 of x minus L times x times P sub L of x. Just two more of these things. 2L plus 1 times PL of x equals P prime sub L plus 1 of x minus P prime sub L minus 1 of x. And last but not least, at least on the examples we're going to cover, 1 minus x squared P sub L minus 1 prime of x equals Lx P sub L minus 1 of x minus L times P sub L of x. These are not the only recursion relations that can be derived from the generating function, but it gives you an idea what recursion relations are. They're ways to determine other Legendre polynomials from information you already know about Legendre polynomials. And this can be ratcheted up basically to infinity. By just starting with Legendre polynomials 1 and 0, which is just the 0th Legendre polynomial is 1, and the first order Legendre polynomial is x, we could use this first recursion relation to find all future Legendre polynomials one step at a time. That's actually what one of your homework problems is. Another use we could have for the Legendre polynomials is expanding a potential. Specifically, expanding a potential of the form V equals K over D. So this is the 1 over R potential you see a lot in physics. The electrostatic potential, the gravitational potential, all of these have 1 over R relationships. So for an appropriate value of the constant K here, this is an electrostatics problem, or this is a gravitation problem. So for example, if this were the electrostatic potential that we're talking about, or the electric potential, K would be equal to, let's see, the Boltzmann's constant, K times Q1 times Q2. Or if this were equal to the gravitational potential, K would be equal to big G, the gravitational constant, times mass 1 times mass 2. And it will turn out that we can write this potential in terms of a linear combination of Legendre polynomials. And we want to show how this is possible. So first I kind of want to draw the situation we have here. We have our origin, and we have two objects that are interacting. One of them I will put up here and call object 1, O1. The other one I'll put over here and call O2. And these two objects are going to interact with each other. And that interaction is going to be a function of this distance d between them. So we're all big boys and girls and physicists or mathematicians, so we're not afraid of vectors, and we're going to define this distance d in terms of vectors. I'm going to call the vector displacement of object 1 from the origin big R, and the vector displacement of object O2 from the origin as little r. And that will mean we can define this d as a vector, and we can say that if we want to know the value of d, because we're going to need it for this equation, well, d's magnitude is going to be equal to the magnitude of big R minus little r. And this is because, as we can see from vector addition down here, little r plus d equals big R. So we just turn that around to solve for d. D is big R minus little r. And we need to know the magnitude of this. Using the law of cosines and defining this angle right here as theta, we can find the value for the magnitude of d. It's the square root of big R squared minus 2 big R little r cosine theta, plus little r squared, all under the square root. So we can get a little clever with how we define this. D, our magnitude. We're going to pull an r out front. Square root of 1 minus 2 times, this time, little r over big R, cosine theta still, plus little r over big R quantity squared, all of that under the square root. There we go. So, might not seem like we've made much progress so far, but this will actually be very helpful, because now we can write v as k over d, so k over r, big R, times this whole term that was under the square root before, oops, don't need that. So I'm just going to write that square root as a negative 1/2 power. Now I don't have it on the screen anymore, but hopefully this form starts to look a little familiar. This is what a lot of physics is being at least familiar enough with standard equations to recognize them when they come up. To be able to see that we can write our potential here in terms of our generating function, we need to be familiar with our formula for our generating function. So I'm going to put it up here just to remind us of it. Our generating function of x and h was 1 minus 2xh plus h squared all to the negative 1/2 power. And wouldn't you know it, all of this right here looks an awful lot like that. And this is the logic behind why we pulled r out of our square root here. It's because we want our first term to be a 1. So, if we get back to the right page of my notes here, if we let h be r over r, and we let x be cosine theta, that means we can write our v as k over r times 1 minus 2hx plus h squared to the negative 1/2 power, or k over big R times our generating function. And here's why this is helpful. Here's why you would want to do this to begin with. Because we know we can write our generating function as a linear combination of our Legendre polynomials. And since our potential v is just some constant times the generating function, this means we can write v as a linear combination of the Legendre polynomials. I will be using lincom as an abbreviation for linear combination fairly frequently going forward. So, since we can write v as a linear combination of Legendre polynomials, that takes the following form. We take k over r, that same constant, and our generating function can just be written as L equals 0 to infinity times HL PL of x. Or plugging back in our values of h and x for this problem, we end up with, not an equal sign there, the following expression. We end up with r to the L times p sub L of cosine of theta. There's that Legendre polynomial of a cosine of theta term that I'd said you'd see in quantum mechanics. You apparently also see it in electrostatics. And rewriting this just to keep coefficient k out front, we can combine this all into one term by keeping everything the same and just absorbing that extra power of big R into the denominator. So we have now written our potential as a linear combination of Legendre polynomials. And polynomials are so much easier to work with, so this will probably make our life easier going forward in further analysis of this problem, which again is not something we're going to do here right now because that's not what this class is about. But knowing that you can write something like a 1 over r potential as a linear combination of Legendre polynomials gives you additional avenues to explore when you're trying to solve this problem. One other thing that's useful to note here, kind of running out of colors, is one of the approximations that can go with this. In the limit that little r is much, much smaller than big R, then only a couple terms are necessary. Which can be very helpful. So little r is much, much smaller than big R means the distance between the two is going to be much larger than the vector little r. So then from here, you could go on to do other problems that are related to this potential. And I just want to at least point towards where these are in the book. So more information can be found in Chapter 12, Section 5. We've basically just done example 1, but there are 2 or 3 more examples that could be helpful here. Example 2 tells you what to do if you have a large number of charges rather than just one individual charge. And example 3 then goes through what you do with a continuous charge distribution rather than a discrete charge distribution. I did just notice that I made a mistake in that down here, what I called object 2, this is the actual object, or in this case, a charge, if we're talking about an electrostatic potential. Object 1 up here is not actually its own object. It is what I call in my other class the test location. So, contrary to what I said before, and my apologies for the error, but we were finding the electric potential at this location, specified by vector big R, caused by the object at position little r. So just a clarification there. My apologies for the error. So that's all we're going to talk about to do with the generating function. The next thing we have to do here is talk about orthogonality and normalization of the Legendre polynomials. We've already shown that the Legendre polynomials can be combined in a linear combination to represent different kinds of functions. And in this sense, the Legendre polynomials, LP, are a set of basis functions. Because we can write some function f of x as a linear combination of Legendre polynomials, at least some functions. I want to compare and contrast this with the unit vectors. Our unit vectors in Cartesian coordinates, x hat, y hat, and z hat, or I hat, j hat, k hat if you prefer, are also a set of basis somethings. They aren't functions, they are a set of basis vectors. And we can write any arbitrary vector A as a linear combination of these unit vectors, x hat, y hat, and z hat. So the same way you can combine x hat, y hat, and z hat to make any any vector you want, you can combine our PL of x to make just about any function we would like to create. But there are some other aspects of our basis functions or basis vectors here that we want to make sure the Legendre polynomials also obey. One of them is orthogonality. Our basis functions are generally orthogonal to each other if we have as few of them as we can possibly have. In terms of our vectors, this means that they are literally perpendicular. X hat dot y hat is 0. Y hat dot z hat is also 0. And x hat dot z hat is 0. But x hat dot x hat equals 1. Y hat dot y hat equals 1. And z hat dot z hat equals 1. And we want to see if our Legendre polynomials obey similar properties. So it will turn out that the Legendre polynomials are orthogonal, but not in as straightforward and literally geometrical of a way as the unit vectors in Cartesian space are orthogonal. The way in which the Legendre polynomials are orthogonal is that if you take the integral from -1 to 1, the range over which the Legendre polynomials converge, of one Legendre polynomial, PL of x, with another Legendre polynomial, PM of x, over x, you will get 0 for all L that are not equal to n. This feature right here that I've circled in green is similar to our dot products of our unit vectors being 0 when you take any two different unit vectors, their dot product is 0. When you take any two different Legendre polynomials and integrate them from -1 to 1, you also get 0. It does not matter whether L and M are even or odd. All that matters is that they are different numbers. So, as a corollary to this, this means since any polynomial can be written as a linear combination of Legendre polynomials, this means if we take the integral from -1 to 1 of PL of x times any polynomial whose largest power or degree is less than L over x, we get 0. So, for example, just to kind of show you what's going on here, -1 to 1 of P5 of x times some polynomial of degree less than L. So it means we can have up to the 4th power. So let's take 4x to the 4th minus 3x cubed plus 2x squared minus 1 plus 6. Oh, those are some mismatched parentheses there. Oh, why are you like this? Minus x plus 6 with a matching parentheses. There we go. So the point is that you can write any polynomial as a linear combination of the Legendre polynomials. And generally, you just start with the highest order, the x to the 4th term, and work your way down. And this is actually a homework problem, so good luck with those, but they shouldn't be too difficult and are illuminative about what I'm talking about right now. So we can write this Legendre polynomial, or not this Legendre polynomial, this regular old polynomial, 4x to the 4th minus 3x cubed plus 2x squared minus x plus 6, is a linear combination of P0, P1, P2, P3, and P4. And then we could split this integral up. So we would have an integral from -1 to 1 of P5 times just the P0 terms. Well, because of our orthogonal relationship between the Legendre polynomials, the integral of P5 times P0 is 0. And the integral of P5 times P1 is 0. And P5 times P2 is 0. And so on up to P4. So this would be 0. The only way this would change is if this polynomial in here is of degree 5 or higher in this example. So if we had added an x to the 5th term to this integral no longer evaluates to 0. So, one thing we haven't really covered yet is how this aspect of basis functions or basis vectors applies to Legendre polynomials. So any unit vector dot producted with itself gives us a value of 1. And there's something related that to this that the Legendre polynomials will obey, and it involves the idea of the norm of a function, which is used in normalizing any function. So the norm of a function, defined as capital N, is the integral from a to b. So this is the norm on the interval a, b. So the integral from a to b of the function a of x as an arbitrary function dx, and that will equal n squared. So I need to make this clear. The norm of a function, just need to write this out. The norm of the function a of x on the interval a to b is n. And we can find n by solving for it from this relationship. So from this, we've got some sort of implicit normalization of the Legendre polynomials. And we already know why or how the Legendre polynomials are normalized. They're normalized so that PL of 1 gives you a value of 1. But what does this mean when we take this integral and L equals m? So it will turn out that if we take the integral from -1 to 1 of PL of x times PL of x, so let's just put a squared there, dx, you get a value of 2 over 2L plus 1. Which means, let me check something in the book real quick. So this means that the norm of PL of x is going to be equal to the square root of the result of this integral. So the square root of 2 over 2L plus 1. That can give you some information about how the Legendre polynomials are normalized. So all of this can be written as one equation. By all of this, I mean this equation right here and this equation right here in the following form. The integral from -1 to 1 of PL of x times PM of x dx equals 2 over 2L plus 1 times delta subscript L subscript m. So I know we just learned about the Dirac delta function, and here is another delta function. This is called the Kronecker delta. The Kronecker delta is a pretty simple valued function, but it's useful for when you want to write a bunch of things all in one equation. It has a value of 1 if L equals m, and it has a value of 0 if L is not equal to m. So this is a way that we can put both of those circled equations into one single equation. If L is not equal to m, the Kronecker delta is 0, and we get that the integral is equal to 0. If L is equal to m, then we have the situation here in pink, and we get a value of 2 over 2L plus 1. Some of your homework problems involve finding the norm of a given function on a given interval, and those shouldn't be too challenging, but you can refer back to the definition of a norm right here in order to do those problems. That is all I have from you, or have for you, for today. Again, don't forget about the assignments that are due, and the assignments that are due next time. That's it for now. Thank you for watching, and have a good day.